In this lab, we are investigating the relationship between current, magnetic field, and magnetic force.
The main problem of this investigation was to figure out what factors affect the rotation of a wire loop within an electric motor. Our goal was to test how changing the number of batteries changes the magnetic force and how that magnetic force alters the rotation of the wire loop. We hypothesized that increasing the number of total batteries within the circuit will increase the revolutions per second of the wire loop. Our results show that as we introduced more batteries, total voltage and current through the circuit also increased. This increased the magnetic force, increasing the revolutions per second of the wire loop.
Magnetic force can be calculated by taking the cross product of the current multiplied by the length of the wire and the magnetic field created by the magnet. Current times length can also be swapped with charge times particle velocity. Each component of the equation, magnetic force, field, and current and length, must also be perpendicular to each other at all times.
The procedure for this experiment started with assembling a wire loop from coated copper wire. On one end of the loop, half of the coating was scraped off, and then a metal support stand was assembled for the loop to set on. A fixed number of magnets were placed under the loop to create the magnetic field. The metal support stand was then connected to two batteries to create a circuit. Current was then sent through the circuit and the loop began to spin. 3 batteries were connected and then followed by 4. Motion of the motor was recorded on an iPhone slope motion camera for data analysis.
To conduct our experiment and analyze the data, we had to assume that increasing the number of batteries through the circuit will also increase the current. This is because increasing the number of batteries increases the total voltage, and according to Ohm's law shown below, voltage and current are directly proportional. Since the resistance of the circuit was constant in each trial, increasing total voltage will increase current.
In our system schema, we have batteries, the wire loop, and magnets. Current flows through the wire loop and is a magnetic field on the wire loop. This magnetic field and current flowing through the wire loop creates a magnetic force.
Another model to visualize our setup is to use a circuit diagram. Between the 3 circuit diagrams shown, you can see the difference between 2, 3, and 4 batteries within our circuit. To understand how the wire loop rotates, let's look at the forces acting on it. On the left, we see a magnetic field established by the magnets below the wire loop. At the top of the loop, when current flows from left to right through this magnetic field, using the right-hand rule, this establishes a magnetic force going out of the screen. At the bottom of the loop, as the direction of current flows from right to left, this establishes a force going into the screen. The direction of this force on different parts of the loop causes the loop to rotate. On the right, we see no current flowing, and using our equations, we can see that this will allow no magnetic force. When understanding why we strip one side of a coated wire, we first need to know what will happen with an uncoated wire. In this setup, when the wire makes a 180-degree turn, the direction of current flow inverts, causing the direction of magnetic force to invert as well. This would not allow the loop to spin, but to shake in place. With a coated and stripped wire, the stripped side is in contact with the wire supports, but when the wire makes a 180-degree turn, the coating is in contact with the support wires, stopping the flow of current. This flow of current makes the magnetic force no longer applied, and momentum carries the loop until the uncoated side is in contact with the supports again, restoring current and the magnetic force. We imported our slow motion videos into Tracker software for data analysis. Tracker allowed us to count the total video frames elapsed over 25 rotations of the wire loop under the various currents. The total frames is within the red circle in the diagrams. Once we knew how many video frames passed during these 25 revolutions, and we also knew that 240 frames per second were shot by the slow motion camera, we were able to use stoichiometry to figure out the revolutions per second of the wire loop in each of the 3 circuits. We compared this to the total number of batteries within the circuit, and we were able to see a directly proportional relationship between the number of 1.5 volt batteries and the loop revolutions per second.
One of the errors and limitations with our setup was that the loop was too big to fully support itself, which would lead to it having a harder time rotating. Another error was that the loop would wobble around on the stands, which would lead to the current being cut off when it shouldn't have. We also didn't measure the current with an ammeter, which would have given us a more accurate correlation between current and magnetic force.
So the difference between our motor and a brushed DC motor is that a typical brushed DC motor, the current flips while it's rotating, while ours just simply shut off current. And also, our setup only had a force acting on it during 180 degrees of the revolution, while a brushed DC motor always has a force acting on it throughout the revolution.
And the brushed will spin faster.
In conclusion, we found through our experiment that increasing the current by increasing the voltage in the circuit caused an increase in the RPS of the loop. The higher RPS shows that there is a stronger magnetic force acting on the loop.